I am Sunil Deshpande and we are going to discuss some problems connected with rotational motion. I always have a feeling that this chapter is what the students find it very difficult to grasp, and quite naturally because there are many types of varieties of problems that we will come across in this chapter. We have problems on finding of the moment of inertia, we have problems on conservation of angular momentum, we have problems on pure rolling, we have problems on slipping, fine. So, we have got many varieties of problems here. We have problems on combined rotation and translation, pure rotation, but anyway I think we have I have just attempted with my series of simple as well as slightly complicated questions to make you understand the subject as thoroughly as possible, fine. So, let us just go through all the problems and enjoy the session. So, this is a problem on radius of gyration, but let me just brief you first about what is this radius of gyration. See, he will have given you a body and a particular axis. So, you are supposed to know the moment of inertia of that body about that particular axis. Now, the question is, at what distance should you imagine this body to behave like a particle so that it will have the same moment of inertia as given, right. So, that distance itself is going to be called as the radius of gyration. So, what did I say? You will be first given one body and one axis, and you should know the moment of inertia of that body about that axis, fine. Say that is I. Now, the distance at which this body has to be imagined like a particle so that it will have the same moment of inertia as that what you have written, like that is I. So, that distance is going to be called as the radius of gyration. So, I equal to m d square, because how do you write the moment of inertia of a particle of mass m at a distance d from the given axis? M d square. So, I should be equal to m d square and d should be equal to under root of I by m. This is what is radius of gyration. So, let me read the problem for you first. The ratio of radii of gyration of a circular disc to that of a circular ring of the same mass and radius about their respective axis is to be found. See, both are of the same mass and same radius, and what does he mean by about their respective axis is, I think if you take a ring, the axis that we always consider is the one which is perpendicular to the plane of the ring and passing through the center of the ring, and so is the axis even for a disc also. So, if you take a disc, the axis should be passing through the center of the disc and perpendicular to the plane of the disc. So, we will write the moment of inertia about these two axes for the two given bodies and equate them simply to m d square. So, we will get the value of radius of gyration for both. So, let me first write radius of gyration for the circular disc. So, what is the moment of inertia of a circular disc? It is m r square. So, I equal to m r square, and that I am going to write as m d square. So, m gets cancelled and you get d equal to r. So, radius of gyration of a circular ring is equal to the radius of the ring. Now, I will write the radius of gyration of the circular disc. What is the moment of inertia of the circular disc? It is m r square divided by 2, and that is equal to m d square again. Let me call this d as d1 now. Mass and radius are same, moment of inertia is going to be different. So, m gets cancelled and you get d1 equal to r by root 2, fine. So, I have written the radius of gyration of the ring and radius of gyration of the disc. Now, he wants the ratio, but we have to be very clear about writing the ratio. See, he wants the ratio of disc to ring, right. So, disc is this, ring is this. So, if you take the ratio, it is 1 is to root 2, and that makes your C option perfectly correct. See, this divided by this will give you 1 is to root 2. I hope I have made my point clear. What is the radius of gyration and how to really write it for the given bodies. Okay, so here is one more problem on finding of the moment of inertia. A thin rod of length L and mass m is bent at its midpoint into two halves such that the angle between them is 90 degree. See, this is to be underlined. the angle between them is 90 degree. So, definitely there arises a question, what if the angle is not 90 degree and if it is 45 degree, 60 degree, 30 degree, does our answer going to depend on the angle between the two halves? The moment of inertia of the bent rod is to be found about an axis passing through the bend and perpendicular to the plane defined by the two halves. See, please remember that whenever you try to find out the moment of inertia, don't just keep on saying find the moment of inertia of this body or that body like that. So, you will have to be always particular about the axis of rotation, because moment of inertia always depends on the axis of rotation, right. So, how does he plan here to take the axis? Through the bend and perpendicular to the plane containing the two portions. So, let me draw the two portions first. So, say this is one part and this is the other part. This was originally a single rod of length L and mass m, but you have bent it so that the angle between them becomes 90 degree, and these are the two halves. So, the mass of this should be m by 2 and the length should be L by 2, and the mass of this should also be m by 2 and the length is L by 2. Now, this is the axis about which he wants you to find out the moment of inertia. Fine. So, I hope you remember that we have a standard formula for the moment of inertia of a rod about an axis passing through its center of mass also and about an axis passing through one of its ends also, but axis taken perpendicular to the length of the rod. So, I will write the moment of inertia of this rod about this axis as well as this rod about this axis and add them. Being a scalar quantity, I will directly add the moment of inertia in order to get the total moment of inertia of these two halves. And I hope in this discussion you realized that this angle does not play any significant role at all. So, whether the angle is 90 or 60 or 30, it does not matter. It is like writing the moment of inertia about an axis passing through the midpoint and perpendicular to its length, because this is the midpoint, remember. So, I will first write the moment of inertia of this rod about this axis, which will be m by 2 into L by 2 whole square divided by 3. So, 1 by 3 m L square is the moment of inertia of one rod plus one more. So, I will multiply it by 2. So, if you solve this, you will get the moment of inertia of this bend about an axis perpendicular to the plane, which will be m L square by 24 into 2 means 12. So, it will be m L square divided by 12. And as I said, this is nothing else but the moment of inertia of the rod about an axis passing through its midpoint and perpendicular to its length. I hope you realized this. It's a very, very important problem, and the correct answer is m L square by 12, which is your option C. So, there is a beautiful problem here on moment of inertia, but you will have to have a little bit of patience here because it is slightly complicated. So, let me read the problem for you first. Mi of a uniform disk about a diameter is I. Its mi about an axis perpendicular to its plane and passing through a point on its rim is to be found. See, you people must have remembered the moment of inertia of a disk as mr square by 2. But remember, there the axis that you will have taken will be by default the one passing through the center of the disk and perpendicular to the plane of the disk, right. Okay, but you do not know what is the moment of inertia of a disk about a diametrical axis. So, you will have to find it out first, and then only you can, I think, use the second part in order to solve the problem. So, what I will do is first apply perpendicular axis theorem in order to know what is his I. But let me brief you something about perpendicular axis theorem also. One strict warning about that theorem is perpendicular axis theorem has to be applied only for a plane lamina. It should never be applied for a body, and here you can consider this to be a thin disk. It is a uniform disk already given. You can also imagine the thickness of the disk to be negligible. So, it is a very thin disk. So, it is a plane lamina, and you can go ahead with your perpendicular axis theorem. Okay, what does it say? If you know the moment of inertia of a thin lamina about an axis about two axes rather, which are perpendicular to each other and in the plane of the lamina. If you know the moment of inertia of a thin lamina, plane lamina, about two axes which are perpendicular to each other and in the plane of the lamina, then by adding those two, you get the moment of inertia about a third axis which is perpendicular to the plane of the lamina and passing through the point of intersection of those two. Fine. So, what I will do is, I will imagine the disc to be like this and the diametrical axis that he is mentioning to be these. See, these are the two axes and they are symmetrical. That is, the moment of inertia about this axis is say I1, the moment of inertia about this axis should also be I1. This is what I mean by symmetry. They are perpendicular to each other also. And now, if I add these two, I will get the moment of inertia about a third axis which is perpendicular to the plane of the lamina, that is this one, and passing through the point of intersection. So, the two axes are going to intersect at the midpoint of the disc and this is the axis I have taken which is perpendicular to the plane of the disc. So, I1 plus I1 is 2I1 and this you have already by hearted, it is mr square by 2. So, I will write 2I1 equal to mr square by 2 or I1 is mr square divided by 4, right. This is his I. The mi of a uniform disc about a diameter is I, and we have already found out the moment of inertia of a disc about any of the diameters and we had called it as I1, but his I is our I1. So, I will write this as I. Fine. So, one thing is known. Now, what he is asking is again the moment of inertia about an axis perpendicular to its plane and passing through a point on its rim. This also we do not know, we will have to find it out and the answer has to be expressed in terms of I. So, here you are supposed to use parallel axis theorem. So, let me remind you something about parallel axis theorem also. Parallel axis theorem can be very well applied for a solid body. You need not have to strictly apply it for a plane lamina like perpendicular axis theorem. You can go ahead even for a solid body also. And now, imagine the disc, right. What does parallel axis theorem say? Parallel axis theorem gives you the moment of inertia of this disc about an axis which is parallel to the one passing through the center of mass. Okay. So, if this is the disc and this is the center of mass of the disc, you can imagine the axis to be passing through the center of mass and you already know this moment of inertia, it is mr square divided by 2 and you want to write about this axis. So, using parallel axis theorem, I will try to write it. See, this is the disc again, this is the center of mass, you know the moment of inertia about this axis which is mr square divided by 2 and now I want to write the moment of inertia about an axis passing through one point on its rim. You can read it here, through a point on its rim. So, I will shift the moment of inertia from this axis to this axis using parallel axis theorem. And what does it say? It is mr square divided by 2, which is the moment of inertia about this axis, plus mass into distance square, this distance. Between the two parallel axes that you are considering, that distance can be radius of the disc. So, mr square, and that makes it 3 mr square divided by 2, right. Mr square by 2 is the moment of inertia about an axis passing through the center of mass and you want about this axis. So, you have shifted using parallel axis theorem. So, Ig plus m into distance square. Distance fortunately happens to be the radius here. So, 3 mr square by 2. Now, this 3 mr square by 2 is what he wants, but none of the options are reading as 3 mr square by 2. You have to express the answer in terms of I. So, what I will do is, I will try to get the value of mr square from here. I is mr square by 4. So, mr square by 2 is 2I. Mr square by 2 is 2I. Therefore, 3 into 2I makes the answer 6I. See, mr square by 2 is 2I. So, instead of mr square by 2, if you substitute 2I here, the answer is going to be 6I. So, what is the answer? C is the correct answer. I hope you enjoyed this problem. It is slightly complicated, I had told you earlier. It involves, what is the beauty of this problem? Why did I take this? Because this involves parallel axis theorem as well as perpendicular axis theorem. Unless the student is aware of both the theorems, he cannot solve this problem.